Hi! In this small clip, I would like to show you all the new features that we introduced in version 2.5 of our finite element software NACS. So what I'm going to show you is changes in the simulation core as well as changes in the graphical user interface. We will start with the changes in the NACS core. So at first we've got a new analysis mode, and this is a new modal analysis solver that allows you to obtain all eigenmodes in a certain frequency range. This is what we have introduced here. And for all our modal analysis solvers, we now can provide you the result of the modal masses as well as the participation factors. And those are computed by using a unit load onto all nodes of the mechanical system. Unit load means that we've got a unit excitation in all degrees of freedom in one direction, and then we see the answer of the system. So this is the new analysis mode available in NACS 2.5. In the magnetical physics, we have now the possibility to prescribe magnets, so permanent magnets, and those are defined by providing the remnant flux density of the magnet. And concerning the results, we can now provide you the dynamic inductance. Previously we could also only provide the static inductance, but of course for transient simulations the dynamic inductance is the quantity that you might be interested in. So this is now also available starting NACS 2.5. Concerning the magnetomechanical interaction, the coupling, we've got two new coupling convergence criteria, and this is the magnetic vector potential and its first derivative, and this allows you to specify more convergence settings, more detailed convergence settings than in previous NACS versions. We also could improve the performance of NACS at 2 points. The first point is the computation of Biot-Savart coils. Here, if you've got the same electric excitation signal on several Biot-Savart coils, this can be right now taken into account, and those can be shared. This was a large improvement of performance. And also concerning mesh interfaces for the non-conforming meshes, here the computation of the cut cell grid can also benefit from the parallelization. Another thing that we introduced is that boundary conditions can now be defined in several ways. Up to now, boundary conditions were defined by defining certain expressions, time-dependent, space-dependent, or frequency-dependent, for example. They could be specified in the graphical user interface or in the script. Now we can also define boundary conditions, and the values are read from either a previous analysis step, or they are read from an external result file. And I have two examples where I can illustrate when this is reasonable. So the first example is a power transformer, and you can what you want to do is you have a coil vibration, and then you're interested in the radiated sound field right here around the transformer. And in order to obtain that sound field, at first you have to compute the tank vibration resulting from that coil vibration. This can either be done all in one simulation, or maybe due to memory limitations or other limitations, or maybe if you just are interested in the acoustic sound field later, then you can right now do the following. You just split that complete simulation in two parts. First part is the excitation of the coils, and then you obtain the tank vibration. First step. Second step, you take the tank vibration and compute the resulting outer acoustic sound field in the air. So this can be done either by prescribing or taking the values from a previous analysis step, or by reading the boundary condition from an external result file. Second example is an ultrasonic flowmeter. That's depicted right here, and here you can see this is supposed to be a pipe. Here the red thing is a piezoelectric sender transducer. The yellow thing is the piezoelectric receiver transducer. Here we've got a fluid media that is flowing from left to right, for example, and now you want to see how long it takes an acoustic wave to travel from here, from the sender to the receiver. This can either be done all in one, or you can also split that simulation in several parts. First part here would be voltage excitation of the piezoelectric transducer, and then you obtain the transducer vibration. Then you start with the normal velocity, the velocity of the transducer, and prescribe right here the normal velocity of the acoustic domain. You obtain here the acoustic field inside that flowmeter. It's a transient analysis, and this result is what you use as excitation for the third part to compute the receiving voltage at the receiver piezo. So this has been everything concerning the NACS core features. Now let's go to the NACS graphical user interface. Of course, we also introduced here the support for those 3 different boundary condition definition modes, either by expression as depicted here, by a previous analysis step as depicted here in that widget, or by specifying external result data. We're going to show something how this works in a short hands-on later on. Another thing is what we have introduced, an improved clip function that allows you to dive into your model. This is what we had already previously, but now we do a real volume clipping, so you can really look into your model, what happens in the computation domains concerning acoustic fields or mechanical displacement or something like that. Okay, so this is everything that I wanted to show. Those are all the news concerning NACS 2.5. Now we're going to start short hands-on and show the new features in the graphical user interface. So here we are with our hands-on. I've already opened the NACS graphical user interface, and what we can see here is our simplified transformer model. We can see the model right here, can dive into the model. Here we've got the coil cylinders, coil U, V and W for the excitation. We've got the tank and the tank foot. We've got the oil, and we've also got the air. We already assigned material parameters right here, and what I already defined is a vibroacoustic analysis. 5 frequency steps is what we're interested in. We have assigned the foot and the tank region to the mechanical domain, and we've assigned the oil and the air region to the acoustic domain. Here boundary conditions are defined, as you can see, all in one simulation, everything in one analysis step. We've got the acoustic absorbing free field boundary condition, we've got the excitation of the coils right here, and we also have the fixation of the mechanical module at the foot. Okay, what we want to do right now is we modify the setup and we add another analysis step. And this is a pure acoustic step, also harmonic analysis, the same setup, 5 frequencies is what we are interested in. And now we just change the setup of the acoustical domain. In the first analysis step, we are only interested in the oil. In the second analysis step, we are interested in the air. We change this. NACS realizes that some boundary conditions don't make any sense anymore, like the acoustic absorbing boundary condition. The pressure result is now only defined on the oil because the air region does not exist in the first analysis step anymore. And the coupling interface between mechanics and acoustics with the air and the tank, this doesn't exist anymore. So we apply those changes, and now we modify the referring setup. That means we need some new boundary conditions for our acoustic analysis, an absorbing boundary condition for the second analysis step on that region ABC here on the outer simulation domain boundary. And what we need right now is also the acoustic velocity on the tank surface. We want to prescribe this for the second analysis step, and here we don't use the expression anymore, we use the previous analysis step. And here NACS automatically realized that we can take that result from the first analysis step, from the mechanical domain, and those two groups are available. We use the fluid structure interface right here and press add. Now NACS notifies us that it has automatically added the required result to the first analysis step. This is what we wanted. And now the only thing still missing is that we add the acoustic pressure for the second analysis step for our region air. And so finally, this is all what we had to change. Now we save that simulation, for example, we call it try for a two-step new, and now we're ready for simulating that problem. We could also do another thing. We load our acoustic grid, here the transformer air mesh file. You can see it in a few seconds here on the right side. This is the model that we already know, that we already seen before. We want to do a pure acoustic simulation. That means we are only interested in that region air, made of material air, and now we again specify that we want to do acoustic analysis, harmonic analysis. 5 frequency steps are taken. We take the region air for this analysis, and now we can define our boundary conditions. And this is again the absorbing boundary condition on that group ABC, the surrounding the air boundary. And then we again take the velocity. This time we don't take the expression, we don't take the previous analysis step, but we take the external result data. And that means right now we have to select an external result file. We can try this result. Okay, NACS complains that this result file is invalid because the required result quantity mesh velocity is not contained in it. So let's try another file. Maybe it's in this file. Yes, it's like that. Here we have in the first multi-sequence step, the required quantity was found, and it was found on that region FSI air. That's great. We add it. Last step still missing is that we add the acoustic pressure as result on that region air, and then we are ready for solving that problem. We save it, for example, try for air external result, and this is all that has to be done to carry out that acoustic computation. So this is everything concerning the hands-on. If you've got any questions concerning NACS or Symetris, just visit our website at www.symetris.de. If you've got any questions concerning NACS, just contact us at sales@symetris.de, and in terms of any support inquiries, just write us an email at support@symetris.de. Thanks for watching and goodbye.